introduction. Thank you for the introduction and thank you for being here for the last talk. It's a pleasure to be here in Chicago at IMSI. This is my second or third time. It's always a pleasure to be here. I'd like to really thank organizers for inviting me here. And yeah, my name is Kamal Chaudhary. I'm a staff scientist at NIST. If you're not familiar with NIST, this is the first scientific lab in the United States, established in 1901. There are two centers, one in Gaithersburg, Maryland, and one in Boulder. So I'm from Gaithersburg. And today I'm going to talk about uncertainty analysis of materials AI model. This project is a part of a bigger infrastructure called JARVIS, which is a joint automated repository for various integrated simulations available at jarvis.nist.gov. So before I go in details, I would like to acknowledge our really wonderful team with experts in density functional theory, tight binding approach, molecular dynamics, quantum computation, technological CAD modeling, machine learning, and experimental validation. So this is the outline of my talks. There are four topics we'll be covering. Number one, because it's a UQ workshop, I see a lot of statisticians, so I thought I'll throw some really basic materials modeling thing. So like one or two slides of that. And if you're experts in materials modeling, please bear with me. So a slide on materials modeling, something about Jarvis database. Then I'll talk about AR for materials, UQ with descriptor type models and graph neural network models. And finally, I'll talk about the leaderboard benchmarking. So let's start with materials modeling. So materials, what are materials? When I say the word materials, what does pop in your head? Stainless steel, plastics, chocolates, makeup, what? What does pop in your head? It's a very intriguing question. What are actually materials? And it has really baffled human mind for centuries. So there are some, I have seen some philosophy books which go 6,000 years in Indian and Greek philosophy. And they talk about what's the fundamental building block of a material, and they talk about atoms and so on. However, the first foundational, I feel like description came from John Dalton, 1800. He said, hey, everything is made of a tiny particle called atoms. Okay, but in 1897, about 100 years from then, Thomson says, oh, there are actually a lot of charged particles, electrons. And Rutherford said, oh, hey, no, so there's actually nucleus in the system of atoms. And then just 2 years later, you can see how fast it's progressing. Niels Bohr said, not just charged particles, they actually revolve in a fixed orbit called electron orbitals. And then Schrödinger says, actually, there's a mechanics for this, wave mechanics, and that leads to Schrödinger equation and quantum mechanics and so on. But the quest is not over yet. It's still going on in particle physics, like standard model, quark, quasar, all this high energy physics going on. So what is actually materials? I think still is an unsolved problem. And it's actually a very exciting field to be. This was science, right? But if you want to put into engineering applications, now you have to see how you can apply these methods. So one of the first method is actually using the Schrödinger equation in a, yeah, this works. So in a method called DFT, density functional theory, we heard a few talks about this. But if you had to solve for electrons problem for a simple like this pointer or something, there's a huge number of electrons, right? So you can't actually solve it. So there are approximations. So instead of dealing with electrons, we deal with atoms. So there's molecular dynamics. Sometimes even atoms are too much. So we actually group number of atoms. It's called coarse grain modeling. Sometimes even coarse governing is too much. So we deal with finite element and other high level methods. It can be top down or bottom up approach. And not just theory, there actually you can understand materials at experimental level as well. Now, because this is such an interesting area of research and study, I put a YouTube 7-hour YouTube tutorial, several videos. So if you are new to this field, feel free to check out my YouTube channel, like, subscribe. So there are a lot of YouTube videos there about the basics of materials modeling. So I mentioned there are several multi-scale modeling tools. So we thought of in about 8 years ago, how about we made an infrastructure which can encapsulate most of these methods. So this is what joint automated repository for various integrated simulation is. It combines classical force field density functional theory, machine learning, and several other tools to kind of design new materials. It can kind of work together to optimize or discover new materials. And it was started in 2017, and feel free to check out some of the review articles we have. It's very successful, I feel like. We have about 50 research articles published with this, and 200,000 users worldwide. So just to comparison, Gmail is 2 billion users, so not even close, right? So, but I think given the materials community is a quite successful infrastructure. There are 5 main components. It's not just a database. You need tools. So of course, we have database like density functional theory, force field, which is molecular dynamics, tight binding, and dynamical mean field theory, and so on. But we also have tools like Atom GPT, Align, and DB3Pi, web apps. Sometimes you don't want to have a database, but actually interact with for your own data. And that's what web apps are. Benchmark. So one of the mission of NIST is like benchmark and lead, benchmark and lead, benchmark. And I just keep repeating this word over and over. So it's very important to benchmark before you lead a particular domain of research. Tutorial. So this is very cutting edge research. So how can we bridge the gap between the undergrads and grads and the cutting edge research? So this is why we provide several tutorials and outreach events. So we are having one of them, Artificial Intelligence for Material Science Workshop in July 9 and 10. So if you're interested, feel free to check out and participate at NIST. So one of the infrastructure is Jarvis DFT. It has, we focus on thousands of materials, about 80,000 materials, and we focus on less number of materials, but I guess more high quality data and more number of properties. So you have properties such as improved band gaps, elastic tensor, piezoelectric tensor, superconducting transition temperatures, Seebeck coefficient, defect properties, and so on. And one of the way to interact is on this website. So you can go to the periodic table, right, and click on certain elements like molybdenum sulfur, and it will show you all the materials, and you can again click on this one of the individual, and that will lead you to detailed information. That is fine. But recently we started something funny, really interesting, I would say, is something called ChatGPT Material Explorer. So the idea is you can go to ChatGPT, search for Explore GPT, and search for materials. And suppose you search for, give me all materials with aluminum oxide, right? And it will list you all the materials. It will talk to Jarvis and pull all the data, and not just give you the data, but actually explain what are these properties mean. This is critical for non-domain experts. Like when I say, what is formation energy? I don't know, right? So for now, you can actually talk about these numbers and what does those ranges mean and so on. And not just talking to the database, it has also several machine learning models integrated to it. So suppose you include a CIF file or a postcard file, it will not use ChatGPT, but actually talk to Jarvis and give you machine learning based predictions. Now, the idea is we have heard about several ages of materials, like iron age, bronze, and so many ages are there. I feel like if we can go to something like ChatGPT Material Explorer, type something, and can not just search materials, but actually design, synthesize, and ship me that material, that I would call AI age. I think we are just 10 years from now. So be ready for that. So there are several tools available for this. So this is just overview of the database, which is very critical for machine learning in general, having high fidelity, high quality, diverse data sets, very important. So I think 50% of the problem is just getting high quality data. So we use this data. Now we talk about AI for materials. Now, I want to point out computers like us don't understand physics, chemistry, maths. What they understand in numbers, 1, 0, and so on, right? So how can we make the knowledge of chemistry and physics convert into information that computers can understand? There are many, many ways. So one of the things we started in 2017 or 18 is classical force field inspired descriptor. So suppose you have a system like molybdenum sulfur, right? A system. What I can do is we can take the atomic number of molybdenum sulfur and take an average of it. That one number will represent that compound again. That's chemistry descriptor. And there have been many, many research about this, like MACPI descriptor and so on. But there was no structure feature when we started this field. In this field. So we started this radial distribution function, angle distribution function, and diagonal distribution function, and that leads to 1,500 descriptors for just one material. And that fingerprint is called CFID descriptor. And that's one way to describe any arbitrary material in that compound, right? But sometimes it can be challenging to calculate this dihedral function, angle distribution function, and so on. Sometimes it becomes very slow. So that's why we jump into this field called graph neural networks. So here we represent any atomic structure as a graph, right? So nodes and edges. I'll briefly talk about that. And then last one is Atom GPT model. So GPT models works with text. So you can describe a material like magnesium boride crystallized in this space group, this bond length, and so on. And there's a text description of that model. That can be forward model, like given this structure, predict me properties, or it can be inverse material. This is the property I want. Can you generate in the structure? That's inverse model. I think Taylor talked about it a little bit as well in the talk. So These are three types of representation. And again, I won't say this is we are claiming this is a victory. There are actually a lot of things as a youngster in the crowd. You can improve the quality of the data, information in the physics to improve these models from your physics intuition. So if you want to know about how to apply machine learning for materials, I'll strongly recommend this review article we wrote about 2 or 3 years ago. Recent advances and applications of deep learning methods in material science. This has been cited about 1,000 times in just 2 3 years, which is pretty impressive article. So we talk about how to apply deep learning in 5 different domains, like chemical formula, atomic structure, text, different type of spectra like X-ray diffraction, NMR, and also images like STM, STEM, and so on. And there are other review articles we have as well, right? So I will not go in details for this, but I think you are already familiar with standard neural network. So we can take descriptor and have a model that can predict properties. Or if you have image data, you can use convolutional neural network. Or if you have graph-like data, right, you can represent atomic structure as graph and use graph neural network. Sometimes you want to work with autoencoders where you have image encoding and another image. Sometimes you have multiple steps. So diffusion and reverse diffusion or inverse diffusion. And sometimes nowadays very popular transformer models where you tokenize each word. So for example, in a dictionary, there are about 50,000 to 100,000 words. So you suppose you say, hi, how are you? I'm fine. So you can convert hi, how are you to tokens, I am fine to tokens, and have an encoder decoder model to establish the relations between these tokens. And when you ask a new question like what's the capital of the United States, it will predict the next token, right? So this is the same thing, but we can do for material science. I want a superconductor with hopefully 300 Kelvin temperature. Predict me the structure, right? So it'd be nice one day if you can do this. But that's the idea, right? So now let's, because this is a UQ conference, UQ event, let's talk about UQ a little bit. I don't need to bore you with the details of how important UQ is, but quantifying, managing, and reducing uncertainty is very important. Not just predicting the single prediction, but actually interval is important, and it can be achieved through advanced sampling, computational inexpensive surrogate model, and so on. And there are many, many packages nowadays. One of my favorite is Uncertainty Toolbox. It's a very nice tool to kind of improve the uncertainty predictions and so on. And there are many other tools as well, like UQ Lab and so on. So we heard about this in, I think, Alex talk. There are primarily two types of uncertainty: data uncertainty and model uncertainty, or you can call it aleatoric and epistemic uncertainty. And there are different classes of that as well. It can come from the noise of the model. It can come from the model itself. And we will talk about a little bit how we're gonna solve this problem. Now, for machine learning, for UQ for material science, right? Material scientists do not really have a training on UQ, in my opinion, in the formal way, right? So I think it's very important to understand what are the methods we have on exposure. There are primarily these 5 techniques I can think of. Number one, Bayesian neural networks. I have heard at least 30% or more of this symposium is Bayesian neural networks. So I don't need to explain to you, but I want to point out, given the diversity of periodic table and how they can arrange in atoms and the descriptor and graphs is very can be very challenging and hard to apply this Bayesian type of neural network from materials design. There are other like Monte Carlo dropout, deep ensemble methods. So instead of having one model, have many models, kind of predict the properties and have an error bar. Quantile regression. So instead of predicting the mean using the least square method, you use a quantile loss function which predicts you the prediction interval like upper, lower, and middle value using the median approximation, right? And Gaussian process, of course, there are a probabilistic model and non-parametric and interpretable. So Gaussian processes are great, but if you have more than 50 features, good luck with that. So there are several advantages and disadvantages of that as well. So these are main methods that, and we will be primarily dealing with deep ensemble method, quantile regression, and GPs. So UQ for materials, as I said, is very important. And one of the first paper that our group published is Uncertain Prediction in Machine Learning Models for Materials Properties in 2018. So it's like 7-8 years ago. So I had to refresh my memory of what I did at that time. So actually I was reading this paper this morning. So these models not just predict you the average number, but actually predicts the prediction interval. And the idea is you can have predictions either which can be very precise. That's where we want to be, high precise and high accuracy. But sometimes what we have, very overconfident model, which has very low accuracy but high precision. Sometimes we have low precision, like all over the place, but high accuracy, close to the bullseye. Or this is the case for many properties which we see in materials, which are low precision and low accuracy. So our goal would be, how can we go to the high precision, high accuracy? Even if you're not there, can we understand which of these 4 bullseye or dart the game we are at, right? So that's the kind of the goal you want to have. Now, as you said, the descriptor-based model, we describe a chemical feature using chemistry and structural descriptors, and we believe this could be a unique representation, kind of unique representation of a crystals. Now, we use this descriptor-based model to train different type of properties like formation energy, bulk model, whatever that is almost calculatable with DFT. We have that database from Jarvis, and we probably trained the models on this, and it was published, as you can see, in 2018, so quite old paper. But it's like about 200 citations. It's not too bad, right? And we also have an app, so you don't have to train models and stuff. You can go to the app, have a postcard, and it will predict you the properties on fly. So just as I said, UQ we try 3 types of model. So one is the quantile, one is direct ML, and one is GP type model. So in the quantile, we use the quantile loss function and 3 models which lower, mid, and upper level predictions. And we have 0.84 upper and lower at 0.16. So 68% population we are trying to capture, right? And we can have direct ML model. So what we do is, instead of doing like usual train test split in machine learning, we do train test split. So train 1, train 2, test split. So one model will be the base model, which will be predicting the mean absolute error and so on. Other model will predict the error of that model, if it makes sense, right? So there are 2 models. And third is, of course, Gaussian process. So we didn't take the 1500 descriptors because it's crazy to have GP with that. So what we did is we tried to have some gradient boosting model, and gradient boosting give you the feature importance. We took top 50 feature and then use GP with that, right? So as I said, quantile regression, direct ML model, and Gaussian processes. So I think quantile regression, if you are a material scientist, I think this is a great thing to get started with the quantile regression approach. It's very, very easy to implement. There are a lot of softwares out there. You can have it for a tree-based model, neural network models, super easy to get started. Direct ML models can be also very useful, but because you have to split the data in train 1, train 2 test, sometimes you have data scarcity problem. We always have data scarcity problem, but again, if you have to break it down, it may be challenging. Now, quantile regression is very good for getting aleatoric uncertainty, while this direct ensembling is very good for ensemble, as well. It will give you some insight into aleatoric uncertainty. And of course, Gaussian process are there. So these are the result for bulk modulus, predicting the bulk modulus using the CFIT descriptor using quantile, 3-split, and Gaussian process. Now, if you see this colorful plot, almost like a rainbow color, it gives you not just an error and the prediction on the test set, but also give you the error bar on each prediction. Why? Because we have this kind of loss function, right? And it shows you the quantile-based property error, MAE error, because we have the error predictor model, and how much percentage bound it was captured. So you can see sometimes 64% for quantile regression, 59% for GBDT model, the 3-split model, and 82% for Gaussian process models. And you can see that especially the Gaussian process model was the worst model, unfortunately. With due respect to all the GP experts in the field, I think the quantile and the ensemble-based methods were quite useful for our data, at least for this material data set that we are using. Not just bulk modulus, we train this model for formation energy, exponential energy, different type of band gaps, infrared frequency, and so on. And we try to see where are we in the MAE scale error regime. So you can see for some of the properties like formation energy, yeah, we are close to here, but for some of the properties like spillage, we are like very quite far away, and so on. So there can be some properties which can be very difficult to model itself. This can also give you insight, like my descriptor, my data itself may be noisy, right? It can give insight on that kind of idea. So individual prediction UQ works even when property model is not that good enough. So even if your model is not good enough, have UQ. So I'm glad that there's a symposium on UQ. So it raises awareness of UQ in the material science community. Currently, I see like I'm a associate editor of this Nature Computation Materials, and I see so many papers like take a data set, train test split, boom, there's a paper, right? But I would like to have a UQ pipeline there, right? So not just give you error, but actually the error bar, right? And why is it important? If you go to an industry job, especially for people who are going to engineering application, they don't care really about error. They care about the uncertainty more. So it's very important to have uncertainty estimates. Now, graph neural network, as I said, there's a one way to describe a material using features, but there's another way using graph. So a graph is a collection of nodes or vertices and edges. So you can consider this cute little picture here with silicon and oxygen tetrahedra, and you can represent or distinguish oxygen with silicon with node features like atomic number, boiling point, and so on. Now you have to think about how can you represent the interatomic distance. There are many ways to do this. And suppose you have an atomic structure with 10 atoms and another structure with 1,000 atoms. How can we uniformly represent this to the computer again? So what we use is take all the Rij, the interatomic distances, and put in a radial basis function, kind of a histogram, fancy histogram. And that gives you uniform representation of the bond distances. But now, when we started this field in 2017 or 18, we saw that, and we talked with some of the experts as well, I personally asked this question, how about bond angles and dihedral angles? Because those are critically important for material science application. And the one of the experts said, I won't say the name, but it's like, it should be fine. Deep learning should be able to figure out. But I was not convinced with this. So what we tried to do is how can we include more physics in this model? And that leads us to include angle kind of description in materials. We try at least 5 or 6 different ways to include angles, and some of them are very slow and so on. One of the best we found is something called line graph. And the idea is, if this is a graph which is nodes and edges, you can consider another graph where the edges are the nodes and the edge pairs are the new edges. And this way you can capture angles. Now if you pair line graph, you can capture dihedral angle and so on. So in this way you can capture many body interaction in graph. And that was published in 2021 in the Nature Computation articles. And it has all been cited, like, I think 500,000, 500, not 500,000 times, 500 times. Almost 500,000 would be nice. So this is, as I said, published in this journal for property predictor, like given the structure, given the property, and we beat at that time, all the state-of-the-art model up to 44% improvement in accuracy because of inclusion of the angles. Recently, after 2 years from then, we published this unified graph neural network force field for the periodic table. So the idea is, I don't really want to develop a properties model for each of them. So why don't we have a model that can predict for entire periodic table? So we took the Jarvis data set, the data set we developed, and we took all the energy force pair. And the idea is, now you can do molecular dynamics with this. You can do global structure search or global structure optimization with this for any combination of 89 elements and their combination, of course, with certain accuracy and so on. So when we're developing this model, after we developing this model, we thought, how can we use UQ for this kind of unified graph neural network force field? And that leads to the idea of ensemble-based method of graph neural network. So what we did is, we have the align model, and usually there are like atom embedding, edge embedding, angle embedding, and then you concatenate this, and then you have another neural network, and the readout layer, and from the readout layer, you do property prediction. What we said is, instead of taking the readout layer, have a readout ensembling layer. So instead of having one model, have 3 or 5 different models, and that will predict you 5 different type of prediction, and we can vary different type of architecture, like small model, medium model, large model, and so on. And then we will have some sort of epistemic uncertainty estimate. This is still ongoing work. It should be coming out soon. And this is an example of very common application of this graph neural network force field called energy volume prediction or equation of state, like isotropically expand and contract the system. So you can see around the equilibrium distance here, they are high uncertainty, but if you go away from that, they are lower uncertainty, which is also very important to understand in terms of graph neural network force field. So finally, I would let's see how much time we have. Yeah, fine with time. Yeah. So final thing is JARVIS-Leaderboard benchmarking platform. So when we started this, we were funded about $5 million from the CHIPS Act, and one of the projects we are funded from is called computational metrology, right? So NIST has a lot of standards development for experiments, but really there are not much standard for computation, at least when we started, right? So we started this idea for not just for benchmarking, but have reproducible benchmarking. Why is it important? There's a paper in Nature called 1,500 Scientists Lift the Lid on Reproducibility. And in that paper, it showcased only 0.5% to 30% papers are reproducible. More than 70% papers are non-reproducible. This is insane for scientific community. And this is a very nice article by this Baker researcher. This is also true for material science, right? It varies, of course, on different domains. So we thought, why don't we have a platform? Nowadays, if you publish any machine learning article, you have to have the code availability, data availability. But do you really think it is enough to reproduce the paper if you have code and data? I don't think so. You have to have benchmark availability. a script that if I run it, I'll get completely the entire uh, output of the entire paper. That is the what we want. So I'm again associate editor of NPJ. So all of our associate editor wrote to Nature that we want to have a statement for code, data, but also benchmark or reproducibility statement. And there we would recommend not regulate, but recommend or request people to have benchmark availability statements. And that's the idea of JARVIS Leaderboard. And it has not just AI, but electronic structure, force field, quantum computation, experimental, and several other categories. And many other categories can be included as well, because material design is probably the most diverse field in whatever discipline it can be. And currently we have 322 benchmarks. So not just for pharmacy energy and band gap, but 322 properties and 2,000 contributions all over United States and Germany and so on. And this is kind of a group effort. So whatever national lab you can think of, and most major university part of this. So you can see about 40, 50 authors here. And it deals with electronic structure, AI, force field, quantum computation, experiment. And I'm hoping that people who are expert in this field and who recognize how important is reproducibility will be able to at least put one or two contributions in our leaderboard. So idea is you don't have to publish it before your article acceptance, but when you are done with this, put your data in like Figshare, Zenodo, whatever, put your code in GitLab, GitHub, but put your benchmark, at least even the simple ones in there. And the idea is once you put it there, there are at least 5 national labs. We will try to reproduce the entire leaderboard every few years. And we'll have the uncertainty from that level as well, right? And everything, there are a lot of, if you work with Python, especially, I think most of the people work with Python, there are a lot of dependency issues and stuff, right? Not even every year, I think every month there's something new going on. So having a standard reproducible framework is also something in our mind. So something like a Nix framework or Docker framework and so on, or UV is a new package framework. We're trying to include all of this in the JARVIS leaderboard. And for experiments, there are only certain experiments like PPMS and QPMS, which allow you to have reproducible experiments. And we are trying to store all the scripts to reproduce experiment, right? And the idea is to have the community. It will probably take a few years, and NIST is not, hopefully not going anywhere anytime soon. So we'll be able to have this culture where we'll be enhancing this kind of reproducibility effort. So as I said, not just category, but there are also subcategories. Suppose you have a regression model, a classification model. Sometimes you are trying to predict spectra like density of states, yield spectra, machine learning force field as a category, atomic structure generation like Atom GPT and so on. Those are generative models, text classification, summarization, quantum eigensolver for quantum computation. And it's very easy to add a new category and here. So the idea is once you put it there, the GitHub action kind of combines all the data set, make the website, and send emails to the developers, and we approve it, and it becomes a part of the list. So there are 2 main components of the JARVIS leaderboard, one for contribution and one for benchmarks. Benchmarks must have a well-defined peer-reviewed DOI article with this to have minimum criteria. Currently, we only allow NIST people to have the benchmarks or have NIST collaborators, people who are actually collaborating with us. But in future, we'll have certain more guidelines or kind of how to add a benchmark, right? It can be from experiment to electronic structure, test data set for AI models, electronic structure, analytical results for like quantum computation and other experiments. So that's again the structure of the entire framework. So what you require to add, what you're required to add is a metadata file, the file like who's the author of this, where is a GitHub repository and so on, when was it developed and so on, and a run.sh script, a shell script. So you can have Python, Julia, Rust, whatever code you are using, but it should be part of that run.sh that if I just run that script, it should be able to install all the software, run the calculation, and produce a CSV file, csv.zip file. These are 6 components in the name, some policy we followed, and that will be the output, and we'll be able to merge this with your contribution and evaluate the uncertainty that came from your prediction or your contribution. This is just one of the example. You can see there are at least 20, 30 different models, AI models for predicting formation energy for atomic structure. This is probably the most beaten to death kind of property for material science, formation energy. And this, for example, you can see for each of this entry, you'll have the CSV file. So the ID and the prediction. So you have well-defined train test split, and the prediction from your model, and the ground truth data, and a kind of small script to kind of reproduce this, install this, and so on, and some metadata file. So this was for formation energy. Some recent work came in force field benchmarking, especially all the major companies like Microsoft, Google, and so on. They are developing their own kind of machine learning force field, and every now and then they are like claiming victory. This is done, So we want to have a reproducible, quantifiable, and something transparent benchmark to evaluate these models kind of uniformly. So the idea of CHIPS FF is have a framework that can evaluate like different models with Jarvis and some other data sets, and on not just for formation energy or optimization of structure, but very tricky properties like phonons, thermal conductivity, vacancy formation energy interface. And the idea is anytime you contribute your model, it will be already added in a leaderboard, and you can show where these models lie. So this is the Pearson coefficient, and you can see, for example, where does it lie in this table. And this is just 14 different machine learning forces we try, like AlignFF, ChargeNet, MatGL, MACE, Orb, MatterSim, 7net. So we saw that, yeah, for most of them, it's very easy to predict like error in the lattice parameters. But interestingly, if you go to the bulk modulus and elastic constant, these are not that great, right? And also the timing. So not just the accuracy, but we also care about performance, right? So we saw that, for example, this equivariance model from Meta is like huge, like 10 times slower or more compared to other models. So it's also important to have a good trade-off balance between the accuracy and speed and so on. So this will also be benchmarked. And not just for formation energy, bulk modulus, we try something more sophisticated like surface energy, vacancy formation energy. One of the most critical things for devices is the interfaces. So anything you have is, any device you have is a bunch of stack of layers, right? So how can you model this? So one of the minimum criteria is work of addition, and we saw that most of the machine learning actually, of course, we are not that good at it. So predicting the interface energy. So we showed that there's a room for improvement for example, aluminum oxide interface. So I probably talked too fast. So these are some of the papers we have for this talk. Again, I have a lot of cool things going on in our group, but for UQ people, I think this UQ in machine learning paper, JARVIS-Leaderboard and CHIPS FF is the probably most relevant. You can also, I'm very active, really more active in LinkedIn and X, so feel free to connect. As I said, this is my YouTube channel. I'm trying to bring awareness and increase the awareness of really developing the fundamentals of materials modeling and so on to the community, and so that people don't use it as a black box, just VASP, in-car, postcard, submit, and there's your number. No, I want the community to understand the fundamentals and so on, and that's our goal with that. Again, thanks to the organizers for inviting this wonderful symposium. Happy organizing.
Thank you for the very informative talk. Question from the audience?
This is a very interesting talk. So within your 3 ways for the UQ, the second one, you kind of add this meta learner to learn these arrows. I'm curious why you use half the training data to train this meta learner instead of using the whole training data set to train it.
Oh yeah, because good question. So we use 45, 45, 10 split. So we don't want to, so when we have the base model, we don't want to expose that data when we introduce the error model. So one model which is predicting the prediction, right? And then the ground truth, and you calculate the error. And now we have a model to predict the error from that data set. But now in the second one, we have only error predictor model.
Oh, so these two are separate models?
Yes, these are two separate models.
I see.
Yeah.
How about you consider just imbibe the meta learner model into the initial model? So
that might be also a possibility. Yeah.
Thank you.
But actually, that method works quite well. Actually, we saw that. Don't have to do GP and Monte Carlo dropout and everything. Very simple, very intuitive model, right? It's a very good way to get estimate.
Sorry. So it's really cool, and I think it will be very helpful to us because we were looking for data and problems. So my question is interesting. Maybe how do you encourage people to upload their benchmarks? I mean, it's a little bit of extra work, right? So I'm curious, is there any incentive?
Yeah, incentive, that's a great question. Yeah, currently it's basically based on our collaborators. So at least whenever I'm on the paper, I ask my students to
Okay.
put it there. And at least all the co-authors and so on. But at NSF level and NIST grant level, we don't want to actually enforce it, but actually request it at least that you can do this. Again, we don't want to make rules, but guidelines. Yeah, but that's the only incentive. I was thinking actually to have a hackathon on Amazon gift card.
Yeah.
Something
That
like
might
this.
be a good idea.
So it would be nice.
I have a question.
Yes.
So you have these three category, including GP and quantile. So there, if there's new methods that, would you? So for example, I understand GP has limitations in if you have high dimension, and it doesn't have to be this way of assuming that it's GP. So, for example, there's a new direction doing conformal inference in statistics that it's dealing with uncertainty quantification for any black box model. And it's more like the integration of the first and the second category using quantile as a way to describe uncertainty and with the data splitting in a careful way. We were able to give a guarantees in terms of uncertainty quantification in a more flexible way. So I'm wondering if there's a new direction in terms of that. Would you add another
Of
or
course, I'll
a
be
few
love
more?
to. What's the name? Conformal? What? I don't know this.
Conformal inference, conformal prediction?
Conformal condition.
Conformal prediction. No,
It's,
see, that's the great thing about presenting at this conference. I learned new things. So I think, yeah, the data and all the tools are publicly available, and I'll be more than happy to connect with my students stuff if you want to work on that. Yeah. So we want some of this more uncertainty estimate tools. So
The Gaussian process regression, did you use the isotropic kernels or anisotropic kernels? Do you?
I think we use again this was 8 years, so isotropic. I think.
Isotropic.
Yeah.
Maybe the anisotropic might improve the prediction.
Yeah. Yeah. I think that's a good suggestion.
Any other question from the audience? Right, so that indicate we're going to close. So thank you again. I'll come up for a very nice
Thank you.
talk.
Some final remark. So this wrap up of our entire workshop. So you should receive some emails from IMSI and another survey email. So if you didn't get a survey email, check out your spam folder. It's comes from somebody called Barbara House. It's legit. I just filled out. Okay. So IMSI also sent you another email about I think reimbursement. Did she talk about that? And also about if you made